Hi, Raghavan.
Hi, Farhan.
Hey, Sudeep, how are you?
Yeah, good, good. Farhan, I had one doubt regarding this project. So, whatever the first three steps where you said to describe multiple things, right?
Yeah.
So we just need to write some sentence like it's a theoretical things only, right? It's not any.
Yeah, I mean, you only need to describe things that someone else who's reading your code or going through your experiment, they need to understand. So, for example, there will be a P matrix, right? If you look
Mhm,
at the underlying class, discrete environment class. So, what
mhm.
exactly that P matrix is and what is it storing? So, in a couple of
Okay,
lines, uh, nothing more.
okay, okay.
Then like encode method and decode how they're working, like very short
Mhm.
description to the point.
Okay, okay. Yeah. Thanks, Farhan.
Sure. Okay, welcome everyone. This is going to be our last classroom session. Uh, Again, I will have to wait for a little while to let everyone in. But just a quick reminder that the submission date for the project is very near. It's 21st of May. Now, understandably, if there could be last moment things, other priorities, and if you're not able to, if you think you won't be able to submit by that day, then just DM me, let me know on Slack, or drop me an email, because I just want to keep track of who has finished the like submitted the project and finished the course and who is in the process, because eventually I had to share that information back with the learning team. So whatever your deadline is, tentatively let me know, and please keep working on the project. If you are getting stuck somewhere, let me know. We will start in a couple of minutes. In the meanwhile, we can just grab the code for today's session. So again, on the master branch W4S2, the link is in the chat box. This is going to be the notebook for today. And yeah, let's just wait for another couple of minutes, because we are going to do cover a lot of stuff today. So I would just wait and let everyone join, anyone who wants to join. Right. So the link to the notebook is again in the chat box, and I'm gonna share it on Slack as well. Cool. So we are 5 minutes into the session. Let's start. So get this notebook again. We are going to run everything in Google Colab. This is the notebook. You will see that this is Foolsball version 3. Version 2 was what we did in session 1, where we sort of added some uncertainty to our actions. Now in version 3, we are going to build over those changes. We are going to add dynamism, and other stuff that I'm going to talk about. Please make sure you're able to open the notebook and you're able to save your progress. Um, so, what exactly are we going to do today? If you go back to week 3, we talked about making the environment even more realistic. And one of the things that we did in the last session was to add uncertainty, right, in the actions. So, every time I asked the environment to execute an action, the environment executed that most of the time, but with a small probability, there was a slim chance that it would execute another action, which could be, which is not the desired action, right? And we implemented that in terms of a table. So we just pre-computed all the possibilities. So we knew there were 20 states. We knew there were sort of 4 actions for every state. So we went ahead and computed all the outcome for every state and action pair, and we built a 20 by 4 by 20 table, and we talked about how to use that table. We made changes to the class, the foosball class, so you know so that we can deal with that uncertainty. But outside the class, we saw that there was very few changes that we had to make, right? So we were able to train the same algorithms, we were able to use the same episode based or step based updates, and yeah, so basically the same algorithms trained pretty well, and they were able to deal with the uncertainty. uh, what we are going to do today, again, you will, if you look at the notebook, those changes are highlighted in black, in bold over here, right? So these changes include everything that we did in version 2, but there are new ones as well. So what I'm going to do is, first I will do a walkthrough, which is going to take some time, because there are lots of new things that we are going to introduce, and then we are going to write some code to sort of finish this new implementation, and then of course we will see how to train the algorithm on this new implementation, right? uh, so starting with the description, the first thing that has changed is this line over here. This is already implemented, but we are sort of going to redo this. I'll talk about why that is necessary, but we will take a different approach today. But yeah, the actions are not going to be certain anymore. There is stochasticity, there is uncertainty or unexpected behavior. The other big change, which is new, is that we are going to make the opponents dynamic. Now, exactly how dynamic they will be, I'll come to that in a moment. But we are going to allow the opponents to move around as well, right? Uh, and and the way we are implementing it today is that opponents will be able to move up or down, so as long as they are in the same column. uh, this is only because we don't want to make too many changes at the same time, so we could just have enabled the opponents to move anywhere on the field, or even made them a little intelligent by letting them sense where the ball is, and try to intercept it or try to block it. But we are not going to do any of that today, but we will let the agents move up or down, right? That is one major change, and that changes a lot of other things. Everything over here remains the same. The rules are going to change a little bit. So the first change that is going to happen is that we are allowing a new action that we are representing by X, and X is basically it's going to stand for, holding the ball in the current position. Sometimes you don't want to move to another position, you just want to stay put, probably because you are blocked and you're just waiting, or whatever the reason is, but sometimes you don't want to do that, right? This sort of makes sense, because now when you are allowing opponents to move around, there will be instances where the best course of action will be to just stay put and not make a move until one of the opponents has cleared out or they have made their moves. So we are adding this action. uh, of course, this is already true, the environment is stochastic. There will be a slim chance that something untoward happens, not what you desired. uh, we are going to make one more change, which was, I think, discussed way back in another session, which was, why are we terminating the game every time you there was a collision, right? We are going to eliminate that. We will continue with the game. There is still the same penalty. Whenever you run into a defender, you still get penalized 5 points. But then the game continues. It goes on. You can, in the next step, you can move out of that cell. And because the defender is also, it can move vertically, so defenders can also move up and down. Um, right. This is what I just described, that the opponents can move in their column, so they can go up or down. Uh, the other major change that is just sort of becomes necessary, because now that we have introduced opponents, and opponents can, we have introduced dynamic opponents, it becomes necessary for the agent to be able to sense its environment. uh, so earlier, the only piece of information that the algorithm got, right, q learning or salsa, was the position of the ball, which we were calling the state of the game, because that was the only thing that was changing. But now that players are moving around, we want to include that information, so that the player is not in a blind spot. Because if you exclude that information, then you're just trying to find the shortest path, but the obstacles around the way they are moving around, and it doesn't make sense for them. Like, it's very unlikely that the agent is going to learn anything meaningful. So we are going to allow that, and we will see exactly how capable we want the agent to be, how much far we want it to be able to sense. Uh, but the field setup and everything remains the same. The change is that now at every step the ball can move, and these green jerseys, which represent your opponents, they can also move. The goalpost still remains static at the bottom corner. So I'll execute this thing. Right. And so while this is going on, the one thing that we just discussed, and this is something we need to be aware of before we go and write the code, is that now state has to be composed of the state of the ball, the agent, and the state of the uh, the defenders or the opponents, right? So we need to, the algorithm needs to have that information. The other question, which we will come back to a little later, is how should that state be represented? Because earlier the state was very simple. Uh, it was actually a pair of row and column values, but we just flattened it to a single integer, and that is what we were using. Now we will have to come up uh, with a good succinct representation of the state. We will see what options are there and which one is the most efficient one, but it will be up to us to come up with that encoding. The third point is interesting. So this is asking, is it possible to segregate next state calculation and reward calculation, like we have been doing? So if you remember, there were two different methods. One method just took the current state, and it took an action, and it just gave you the next state. And then you took the current state and the next state, and you computed a reward. Uh, there were these two separate functions that were typically called from within the step function. But now this is likely to change, because there are multiple actions that would lead to the same sort of transition, right? So, for example, when you are here, and if the agent decides to go north, it comes back to the same state, or it tries to go west, it comes back to the same state. And both are these are instances of trying to take the ball outside the field, so you want to sort of have the same reward for both instances. So even if you didn't know which action caused the state transition, you could just have the same reward in both the cases. But now there's a third possibility, which is that the agent just tries to execute the action X. So it just tries to stay put in this position because of something it sensed in the environment, perhaps. And you may not want to have the same reward for that possibility, right? So now the reward is sort of going to depend on the state transition and the action that you took that caused the state transition. So that has to be factored in as well. And then, because there are more than one agents, and this is a simulation of a real game. What could be a real game? So uh, we will have to pause for a second because someone is asking for the link. So did everyone join with the same link that we have been using so far? Because there is.
Like what?
There are two links actually for Tuesday's one and then Thursday, Friday other one. So I faces sometime this problem. I didn't know that there are two links. So, okay, yeah, I think this is Tuesday's link.
Tuesday's link, right? Uh, yep. So the last point I was discussing was atomic. The actions being atomic, which comes into picture because now you have multiple agents, multiple moving pieces, right? So this isn't the real world where everything happens simultaneously. So we have to think about how to simulate that. How if two players are moving to trying to move around, then how do you simulate that? Should we will sort of look at that closely when we look at the code. But these are the questions that we need to answer as we go along writing the code, right? Uh, so this is the foosball class, which is for version 3. There are a few changes. I will walk you through most of the changes. There are some requirements as well, which have to be filled in, like this to do over here. But largely, the code is already done, right? So uh, let me show you what it looks like. So these two methods over here, they are the same. These are from the previous implementation. The only thing is that I have changed their name for the sake of disambiguation, because now there is this is, there are actually different things. So there are individual states, like the state of a player and the state of the opponent, but then there is also the state of the whole environment, which is going up to be made up of the state of the player and the opponent. So instead of, these methods were called to state and to indices, so I've just renamed them to encode indices and decode indices, but the logic remains the same. You take a pair of row and column and convert it to an integer, right? There is a new method that has been introduced over here. I'm going to skip this for the time being. We'll come back to this. uh, then we have declize. There are changes over here. I'll show you what those changes are, but declize still is there. Init, of course, is there. We have introduced this new action, uh, set rewards as it was, reset as it was. The step function has changed a lot, and if you look at the rest of the code, pretty much all the other helper methods that were there, like get next state on action and get reward on state transition, they have been removed. And I'll talk about, I sort of mentioned, right, that now we have to take into account the current state and the next state and the action. So we want to have that logic in one place. We cannot separate it. We cannot have two different functions. So state step has a lot of logic built into it, but most of it is going to make sense. I'll show you the diff in a second. Then of course render is there. Render has slightly changed because of course we have opponents that can move around. So I want to switch over to the diff view where I'll show you what those changes are compared to version 2. Right. This is the foosball class. Like I said, two state and two indices are just they have been renamed to encode indices and decode indices. Uh, Make observation we'll talk about a little later. There was a field where we were capturing the number of states. This has been removed. I'll talk about it a bit later when we have built this class, when we are actually going to update build a queue table and update that, then I'll say why in states is not needed here. And typically this will be the case, like the environment won't tell you how many possible states there are. You need to figure that out. But the sort of major changes are over here. So earlier we had three different variables. There was init state, goal state, and opponent states, and these were all stored within the foosball class. Uh, Now we are not doing that. We still have three variables: player state, goal state, and opponent states, but these are not being stored, and we'll see why. The first change happens over here. The logic is still same because I'm passing this text template which is made up of strings, and you want to convert it into an array representation. So we still have this pair of for loops going with the rows and the columns. And over here, I'm just trying to locate if there is an agent in one of those row column pairs. And if there happens to be an agent there, then I'm just capturing that in player state. And I'm removing or erasing the uh, player from the map, right? Because we want to keep the map and the state and the moving pieces separate, so we can render them whenever we like. That is one that still remains the same. There is sort of no change other than that this is now just a variable local to this method. uh, the change over here, there is a difference because now I am still locating opponents. I'm still appending their position to their state to this list over here, which is a local variable again. But now I'm also erasing that their position, the green jerseys that we had on the map. So I'm also erasing that from the map because now again they are capable of moving around, and I don't want that information to be uh, s- you know uh, stored together, and that will just makes it easier for us to work with the render function. So we already captured their positions in this list, and we can erase that as well. The goal state encoding and everything remains the same. But this line has been added, which wasn't there. So this is something that we need to look at. Yeah. So now this is the init state. If you remember earlier, so the init state was just being set to the current state of the ball, right? Wherever you found the player to be, you set your init state to that variable. Uh, Now the init state is going to be a dictionary because there are three different substates or three different pieces of information you want to include. So this player state, which is again going to be a single integer between 0 and 19, uh, that is going to be stored against agent. For opponents, we are going to store a list which will have five different states, each corresponding to one of the opponents. And for goal, again, there is this is going to be a single integer again. Uh, we don't have a dynamic moving goal, so but this is just provisional. This can be removed for the time being. The problem we are working with, goal is not going to be needed, but I've kept it here so that in future this is just flexible and you can change things around. The rest of the code and assertions are the same, but the major change is basically that now init state is going to be a dictionary of things. uh, yeah, that was a change to your deserialize method. If we talk about the init method, we just added one action over here. Of course, we already introduced sleep probability over here in the last version, in version 2. So that stays with us, but on this line, we introduce a new action, which we are calling X, right? The other change is that in the previous version, we were building a three-dimensional table, and we were doing that with this method, and we're passing the sleep probability to that method. We aren't doing that anymore. We're just storing the sleep probability in this variable, right? And I'm going to come to that in a little bit. Yes, if you look at the reset method, then it is pretty much the same, except that now instead of trying to return self.state, which would be a dictionary like we just saw, it is calling a method called make observations. And because we haven't yet seen make observations, we can skip over for the time being. But what we should remember is that now return is not reset is not returning you the state of the game; it's returning you something else. Uh, this method that we introduced last time, which is get likely next state on action, is not needed. It has been removed. I'm going to talk about that in a minute. The get next state on action, this has been sort of absorbed into the step method. The get reward of on transition, this also has been absorbed into the step method. And yep, is terminal state, that is this has been removed. We will talk about this a little later. But this is no more inside the class. And of course, this step function has expanded. It has absorbed a lot of other logic. This method, which we specifically introduced in version 2, which was used to construct a three-dimensional table, it has been removed. And really the only thing that it was doing is look at every state and action pair, and then look at what are the possible outcomes of that state and action pair, because things were uncertain. There were multiple likely outcomes. So just it would compute the probability of each outcome, that okay, if you are a state 5 and you take as action north, then what is the probability of going up and ending up in state 1 or 0, and what are the small probabilities that you end up to your left or right or to your south. So that is why we introduced this one. We are not going to build a table today, because this table, the good thing about the table is you can just look up a state and action pair, and you immediately get a list of probabilities, and using that probability we would sample from the likely next states. The bad thing is that it will occupy a lot of memory if you the number of states is really big, right? And we haven't yet talked about the number of states, but I can assure you that it is large enough that we don't want to construct the table. And it is still possible to introduce the uncertainty uh, that we were doing using the table, but we won't pre-compute. This was sort of a pre-computation of all the possible outcomes. Now we are going to simulate it every time we take an action. So probably it will be a little slower, but it will occupy less memory, right? Um, okay, I don't want to even talk about render, because this is sort of a black box for us. But now, going back to why we really introduce this method over here, uh, this is because we talked about this change over here, right? So we asked what should make up the state of the environment and the agent now, right? And it's important that we don't keep the agent in the dark, so the algorithm is able to learn something meaningful. So it makes sense to include the position or the state of the agent itself, as well as the position or state of the opponents, right? So these are two things. We are optionally also including the state of the goal. But the other thing that we wanted to do is uh, right. Which isn't really, I think, mentioned here. But the thing that we want to include is more make the environment more realistic, in the sense that if I just provide the agent a snapshot of what the entire field looks like, of course it's going to learn to make intelligent decisions, right? But in a more realistic environment, your agent will only have limited visibility. So don't expect it to uh, be able to know everything about where all the agents are present, where the goalpost is present. So that is something that we are going to experiment with today. And what we want to do is we want to allow visibility to a certain radius. and think of radius in terms of cells. So if my agent is over here, for example, I can let it see the adjacent four cells to the left, right, top, and bottom, or the adjacent eight cells if you include the diagonal, or I can include even more cells. I can make this area larger, but I definitely don't want to include the whole field, right? And that is why you have to introduce the concept of observations, which you will find if you are referring to books or other sources. So we'll often say that there will be observations and states. So observation is what the agent eventually gets to look at. A state could be something larger. A state could be something that is being maintained internally if it's a game, or it would be unknown to us if it is some more complex real world environment. But what we really care about is the part of the state that is visible to us at every time, and that is what we are going to call an observation. And in our case today, we are going to restrict the observation to just four adjacent cells, so top, left, right, and bottom. Right. So now if you go back, yeah. So I mentioned this. The opponents right now have been just programmed. We are going to program them to move up and down randomly. uh, I'll show you that piece of code when I'll talk about the step function in a minute. Show the exact code, but they are going to be able to move up or down as long as they are in the same column. They cannot move left or right. This is an arbitrary choice. We can make make the environment a little bit more complex. Just let them move left and right as well. That will be just a few lines of code. Mm, okay. But yeah, over here in observations, we want to take the entire state, and then we want to only uh, let pass through certain bits of information, which is the player's position and whether or not there is an opponent in the four adjacent cells that we talked about. So only top, bottom, left, and right, or north, south, east, and west. We are not including the other four cells, which would be diagonal right now. This is again arbitrarily. We can also choose to include the other four cells, right? But we certainly want to include this piece of information. This is something that we can tweak and see what impact it has on the agent's ability and performance, how fast the algorithm is able to run, learn, and then we can tweak these things. But I'll go down and walk you through what the step function is like. So in terms of the API, it remains the same. It still takes an action because the state is internally stored, so it doesn't really need the current state. It just takes the action. Uh, then over here, we are basically doing what we were doing with the table that we built in version 2, right? So we're trying to simulate a possible bad action. So this over here, this is the selected action index, which we just get from the, uh, the list of actions. So if my actions are north, south, east, west, and X, then suppose if the action I selected is south, so this is going to be, this index is going to be this. For example, if your action list looks like this, and the action is west, then your index is going to be 2. So this is nothing but converting from that string to an integer. And then we just compute the chance that one of the bad actions happen, which is going to, we are going to take slip probability, which we already stored inside the init method. So we are going to take that and just divide it over all the possible bad actions. In this case, for every action, you will have 4 other bad actions. This is going to be 4 because total number of actions is 5. So we divide by 4. And then we compute those probabilities. So we just build a list of probabilities, pretty much like what we were doing when we were trying to find greedy actions. So very similar to that. There's a little bit of different in the way that this probability is being distributed, but the idea is same. And then using this list of probabilities that we just built from the slip probability and the actions, we are going to pick a random action, which we are going to call executed action. Now, executed action will most of the time this will be the same action that you passed down over here, but occasionally it will be another random action, uh, because that is what we are trying to simulate. Okay, so this was the first step, was just converting, going from the input action to the action that actually gets executed. Then of course we need to figure out where the player are, where the position, where the opponents are, where the goal position is, and we just get that from the state variable, which is a dictionary. So we get these three out separately. Uh, then the next step is to simulate the player's movement. Again, we just use the decode indices to go from player's position, which we computed over here, and then I go to a row and column tuple, and then I find out the new row and column tuple, and then over here I just check that if it's feasible or not. So depending on the action and the current position, I will get to know whether this is feasible or not. If it is feasible, then I store the new position. I again encode back from the new row and new column back to a single integer. I call it new player position, and there's a flag that I'm setting to false. It's a flag that I'm calling outside. Uh, we will use it later. In the other case, if it's not feasible, again, the older approach, so we just, the new position is just the old position, and we set the outside flag to true, right? So this is only going to happen when you are trying to carry out an outside. So we are setting that flag here. Okay, after that, what you really want to do is simulate the opponent's movement. So first thing I do is create a copy of all the positions, because there are 5 different opponents. There there are there are multiple ways to in which you can update the positions. The approach I'm using here is sequential, so it will take, it will look at the very first player, wherever it is on the field. It will decide if the algorithm wants the player to move around, and if it wants to move around, it will decide what the next position is and figure that out. Now the next player, when we are going to look at the next player, that player will see that the first player's position has changed. The other players are still in their old positions, but the second player will base its decision on the updated position of the first player. And then the third player is going to look at the updated positions of the first 2 players. So this is sequential. Whether or not you exactly want to simulate it in this way, or you want to do parallel updates where you update the position of each player randomly, and then you figure out if there are any collisions or not. If there are collisions, then you sort of want to undo those movements, some of those movements. That will be a little more complex, because this is just a game environment. We are applying it sequentially, right? In terms of code, this is pretty simple. Again, just going over the opponents one by one, and then for every opponent I get its row and column. Then I pick a random action, because the opponent can only have 3 different possibilities. They can go north or south or stay in their position. So I am just randomly selecting, which means there is a 0.33 probability of either of these actions happening. And then based on that random action, I compute the new row and the new column where the agent might end up. And then there's a little bit of check over here, which is the first part. Of course, makes sense that the agent has to remain within the field. But over here, we are then finding, so if the agent can indeed move to the new position, then we are trying to find that new position, and like just encode that new position. So go from row and column to a single integer representing the position, and then we want to quickly check if that new position is already, like if there is already an agent, or if it is a goal post. So we want to avoid those situations where the updated position is going to uh, clash with someone else's position, or the agent goes inside the goal post. So this check is taking care of that, right? And if you look at it closely, then we are checking, this is the updated position of a player, the opponent, one of the opponents, and this is the updated positions of all the agents. Of course, only some of these, this is a list, so only some of the states in this list are going to be updated at any point, and it will depend on the uh, on the order in which we update the positions of the players. Uh, but yeah, this makes sure that two agents do not end up in the same cell and stuff like that. It is still pretty much possible for your opponent to end up in a cell where your agent was. So like in the previous case, the agent could move into a cell where there was an opponent. Now because both can move, then the agent can also the opponent can also enter the agent cell, and again that constitutes a collision, right? Now the reward logic looks a little different. So because there are a few different possibilities. So initially I'm initializing reward to 0, and we don't know if the action is going to cause the game to terminate. So I set the done flag to false. There's a third variable that we're calling normal move. We'll see uh, what that is doing, but this is at the beginning initialized to true. The first thing I want to test is if my new player position, which is the player of the ball, is in the goalpost or not, right? So if it is in the goalpost, if you have scored a goal, then I just uh, we just take the reward, which is +5, and add it to the this variable. Right? Now this plus equal to uh, it's isn't really required here, but I have just used it for the sake of consistency because it is needed in other conditions. But yeah, basically you add it to your reward, and because we just conducted a goal, so done is going to be true. This is not a normal move. By normal move, we mean if you're going to an empty next cell, so that is set to false. Uh, the second condition over here, this is interesting. This is where collision happens. So if your new player position is in one of the new opponent positions, uh, and there are different ways to test for this, and the exact implementation will decide the behavior of the game. But what we are doing right now is that you update the player of the position, you update the player of the opponents, and then you check if both of them have landed in the same state, or you can say at the same position on the field, and then consider it a collision, right? There could be other ways of doing this, but we haven't really implemented that, right? Now this is why this in this case will let us understand why I'm doing a plus equal to over here. So it's possible that, or actually let's look at the next one. But in this case we get the reward for or the penalty for colliding with an opponent, right? And again, this is not a normal move, so it is set to false. um, in the third case, where you are basically trying to go outside, which this is based on the outside flag that we computed here. So for the case of an outside, then we just take the reward for uh, for the outside and accumulate that. And this is practically where it becomes clear why it's necessary to have a plus equal to, because suppose the action you took was, uh, let's say, so you took an action, and yeah, so suppose, yeah, suppose you were in the top left cell, right? And then you took action north, which means you are conducting an outside. So you should be penalized for the action. So that reward should definitely include the penalty that is going for outside. But because your opponents were also capable of moving, so perhaps one of your opponents ended up in your position, right? So they ended up in your cell. You just tried to go outside the field. You didn't go anywhere. You ended up in the same position, but now uh, the other player came over and they ended up in your cell, and that is a collision. So now the game should sort of doubly penalize you because there has been a collision and there has been an outside as well. That is why this plus equal to has to be included over here. So it has to be included over here at least, and we have to think about if it is needed here or not. In case of a normal move, if neither neither of these things happen, if there hasn't been a goal, there hasn't been a collision, there hasn't been an outside, then obviously it's a normal move. Then you just get the reward that we normally do, right? And so they are going from top to bottom. These are the things you first find out what the executed action should be. Should it be the action you pass down? Should it be a bad action? Then you take that action and you simulate the player's movement. Then you randomly move the opponents around, and then finally you work out the rewards based on the agent's movement and the opponent's movement. And this is what you encode in your new dictionary. So now we are overwriting self dot state with a new player position, a new opponent position. The goal position pretty much is same, so it just goes in there. The last thing this method does is again call this make observation helper method, which we haven't implemented yet, but the idea remains the same. Reset was also doing the same, because both reset and step, they have to return the next state. And because we don't want to pass out or return the entire state, we're going to call this make observation methods, which will just retain part of the state, and then whatever that output is, whatever that restricted output is, we are going to pass that along with the reward and the done flag. This is still the same. The only thing that changes is that earlier we would just pass the entire state. Over here, now we're not going to do that. Right? This is how this works. And if we just want to make this class work, then all we have to do is implement this method, make observation. Again, the idea is same. The first thing I do is, this is inside the class, of course, so I can pull out the player's state, which I'm calling player observation, right? So this is the from the dictionary you get the state corresponding to the agent. This is going to be an integer. You convert it back to your row and column. This basically gives you the row and column where the player is. Now what we want to do is, like I said, we want to look at the 4 adjacent cells to the north, south, east, and west, and decide if there is an opponent there or not, right? And we want to take this dictionary, which I'm calling opponent observations. So this is right now it is initialized with none for all 4 cases. But over here, what you want to do is you want to put a 1 over here or a 0. Right? So if there is an opponent, then you initialize it with 1. If there is no opponent, then you initialize it with 0. So at the end, this dictionary is going to have ones and zeros, depending on where the opponent is present or not. Right. So let's go ahead and implement this function. And there are a few changes to the render function as well. You can just look at the diff, or you can read through the entire code, but those are relatively smaller changes, and they are really black boxes for us. So let's try to code this up. This shouldn't take more than a few minutes. So just loop over, find the position of the 4 adjacent cells, check if there is an opponent there or not, and if there is an opponent, then place 1 uh, correspondingly here. If there's no opponent, then put a 0 over here. Okay, this is going to be really straightforward because you just need to take the player position and then add the different deltas like we did when we were figuring out whether when we are just trying to move the player around, right? So in this case, I am using the variable scan row, scan column just to hint that these are the positions that I want to scan for the presence or absence of an opponent. And the first thing I want to do is just check if these are even valid, if they are within the field. So this check is basically that. The other thing that I want to check is if there is an opponent or not, right? So if there is, and that is very simple to do because scan row and scan column, you can again encode it. It gives you a single integer, and you can just look that up uh, in this thing, which is the list of all the opponent positions, all the opponent states. So it's just two lines of code to check whether your the place you are scanning is within the field and it is occupied by an opponent. And if that is the case, then you initialize it with a 1. You initialize the corresponding entry over here with a 1. If that is not the case, so either the position does not exist, in which case there is no question of an opponent being there, or there is no opponent there. So in both the scenarios, it has to be initialized to a 0. Right. This is nothing complex, but now look at what we are returning from here, make observations. This is going to be player observation, which is just one integer between 0 and 20, and a dictionary that maps these four directions with the presence or absence of an opponent. Right, and this is the method that we are using in both reset over here and also in the step method. Right, so we return observation, reward, and this was always the case. The reset only returned you the state. Now it returns you only the observation. The step function gave you the next state. Now it returns you the next observation and the reward and the done flag. The other thing I think I missed is the done flag, which is only being set to true over here when you score a goal. So if there is a collision over here, we aren't setting it to done. So the games are going to go on for a little longer. All right. So with these changes, let's try to run the code. Let's see if there is any issues. There don't seem to be. Yep. So pass the early test. Now let us just try to interact with the environment again. Things have changed now. Last time we did this, the player, there was some uncertainty. Now along with the uncertainty, you also have this capability where your opponents can move around, right? So I just resetted the game, which gave me this output. And thinking, so reset function only gives you the state, the state of the game. And like I said, the state is made up of two things. First thing, the first number, this integer, is the state of the player, which should be 0, obviously, because we are over here. The dictionary part of the state is the position of the opponents. In this case, of course, north doesn't have an opponent, so it's mapped to 0. East doesn't have an opponent because there is no opponent. West obviously doesn't even exist, and south is also clear. So there are 4 zeros. Let's try to take the ball to the east, right? So the ball did indeed go east. Its state updated to 1. Uh, Still, there is no one to the north. East also became clear because this opponent moved out of the way on its own. So east is also clear. So we still have all zeros. The difference is now that earlier we had just reset the game. Now we have taken a step, so you also get the reward, which is -1, which is okay. We just move to an empty cell, so this is -1, and the done flag is false. Right. Now I would take my chances and try to go south. And if you look at the difference between these two states, I tried to bring the ball down to this state, but then this opponent also seems to have climbed up and ended over here. So there's a collision, which you can see the exclamation mark over there. The state is 5. This is 5 counting from 0, of course. Uh, but you can also see that even now this is all zeros, because there is we are not encoding this position, right? We are only looking to the right, bottom, left, and top, so it's all zeros. And that also sort of begs the question if we should include this piece of information over here, like if there is an opponent, probably you need to move out of that cell, right? This will help you with the X action. So if, that is something you can experiment with. But yeah, let me quickly execute east, for example, again. So I moved out of that cell. The agent also, the opponent also seems to have moved down. But now for the first time, we are seeing a non-zero entry over here, right? So north now is 1. The other positions are still 0, which makes sense. The diagonal position, we are not encoding that information in the observation, so that is omitted. Again, something to think about should be, because if you think of a realistic scenario, then probably you want to equip with your agent with information about uh, what is in these cells as well, because this is sort of an imminent threat or challenge for the agent. Because in the next step, if the agent decides to go here, we typically want to know if there is a chance that another agent could be here. So probably you want to include the visibility and include the diagonal cells as well. That is something that needs to be experimented with. But yeah, now we can just go try to go south, south again, right, and south once more. Right, so this terminates the game. You can check that all of this stuff is correct. We didn't really see the bad action anywhere, I think so. We can reset the game and try once more. So let's try going south, south again. Yeah, right. So over here, when I was here and then I tried going south, but I actually ended up east. So you can still check that random actions are happening with a small probability. And if yeah, I mean, we can verify that. And now I'll use Q to stop the execution. But this is sort of a verification that the environment seems to be working according to the rules that we have encoded. So we'll go ahead and override the reward structure. Again, this is optional because this was something that we played with in the beginning, where we said that typically there should be no reward for moving to an empty cell, because this is just something that we want the agent to learn. Uh, but it's up to us. It's up to us because the end goal is uh, so Sudeep, where exactly are you getting that error?
While I'm playing with environment, when I give any specific uh, action, it is giving me like argument of type int is not iterable.
Could you tell me which line number it is? Like you would be seeing which line number inside the foosball class it is.
It's not giving exact line number over there because I'm getting while this error while interacting with the environment. I'm
With the
not
environment.
getting
Yeah.
foosball
Uh,
class is getting compiled properly.
right. That would be compiling, but I'm pretty sure that the error inside. What you could do is, uh, just execute a few steps outside this loop. So create
Okay.
environment and then run it with. Because of this exception
Okay.
catching over here, you're not seeing the full error message,
Okay. Okay.
and it's very likely to be somewhere in the observation make observation method, because the rest of the code is the same between you and me.
Okay. Yeah, I'll check it for it.
Yep. So yes, the other methods we don't really need to change them. Like I said, we only made changes inside the environment, so most of the stuff outside is not going to change. Greedy policy is going to remain same. Pretty print policy. This is interesting because we will see that it becomes a lot more challenging now visualize what is going on, because we'll come back to this a little bit later, but you will see that this pretty print policy is not so useful anymore, because now there are multiple moving pieces. So we're just including it, but probably you will have to rewrite this. Okay. um, Collect random episodes still remains the same. Discounted returns remains the same. The only difference is now that these observations are much different and complex. So this is also going to be same. Right. So at this point, we sort of have a new environment with a different behavior, and now we want to test if we can use the same algorithms that we were using earlier, because we saw that when we made those smaller changes where there was just uncertainty in our actions, there was no movement, or the environment was still static, then the same algorithms were able to perform really well. Right, so we just want to go to the last three implementations that we did. The one, the episode based Monte Carlo approach, where you simulated entire episodes, and the one with temporal difference, so q learning or sarsa. So we want to run these, with the new environment. But now there is a challenge, uh, and the challenge is over here. If you look at any implementations, so you construct a table. First of all, we don't know how many states there are, right? Because all we are getting back from there, from interacting with the environment, is a structure like this. We need to figure out how many possibilities there are. So we'll do the math in a little bit. But even when we know the number of states, so we are able to construct a table with the number of states and the number of actions. When you're trying to fill up that table, right over here, so you want to index into that table using your state and action, right? And our state right now, which we are calling our observation because it is only partial information, so that is made up of something like this. It has an integer, it has a dictionary in it. This is not going to help, so we need to somehow hash this sort of information, or we need to somehow encode this information, uh, so that it becomes a distinct integer. So we still want a distinct encoding for every possible value of the observation, because that will allow us to store values or look up the table through indexing, right? And if we are able to do that, then we can almost use this algorithm as it is. The only thing that is going to change is that we need to substitute something else instead of this s over here and over here, because we cannot use the raw state that you get from discounted return episode, because that state is going to look like this row over here. So it's going to be a tuple of an integer and a dictionary, right? Now, talking of states, so first thing, let's go all the way back up and think of states. So what we do know is that the ball is able to move, the players are being able to move. Now, if we were returning the entire environment, the actual state, even then there are multiple ways of encoding that information. Perhaps the simplest way will be to just take an array of size 20, because there are 20 different positions, and then mark all the occupied positions with a distinct integer. So perhaps you use 0 for unoccupied positions, one for your opponents, one for the agent perhaps, and two for opponents, and three for the goalpost. And which that means is that basically you need to you have an array of size 20 where each position can be either 0, 1, 2, or 3, So four different possibilities for each cell, so which roughly translates to 4 to the power 20 different possible states, right? Which is a huge number. Is 2 to the power 40. Um, that is not what we want to do, because then the table size is going to blow over, and also a lot of those states will never really happen, right? Because there are only five of the opponents at a time, so many of those. If you take an array of size 20, then most of the entries in that array are going to be just empty states. So we want to use a more compact notation, more compact encoding that still represents everything. And at this point we also know that the position of the goal is not being sent to us, and it doesn't even really matter. The only thing we care about is the position of the ball and these opponents. uh, we are The thing that helps us is that we are not even looking at the entire field. So the amount of information we get out of the environment, that is already less than the information that we would have gotten if we were getting the entire field as an array. uh, so what we really are getting is just this tuple that you can see everywhere over here, something like this, and we want to encode it to a single integer, right? How do we do that? uh, Really simple, because if you think about the composition of how of the observation, then you have the state of the player, right? So sorry. So you have the state of the player, and then there's a dictionary with the that has four different bits, right? So it will have a one or a zero, uh, dip, corresponding to north, east, west, and south, right? The player itself can be in any of 20 positions, right? And for each of those 20 positions, there are 16 different possibilities in terms of the presence or absence of the opponents, right? Some of them won't really occur, because if, for example, your player is at the top left corner, then obviously the state where there is an opponent to the north of it, that is not never going to occur during the game, never. But for the sake of simplicity, for the sake of being easily able to encode it, let's consider all 16 possibilities for all positions of the player. There are 20 positions, and there are 16 uh, configurations of the opponents next to the player. So that means the size of the state space, or the number of total possibilities, is 320, right? So we sort of, if you remember, I said that we are going to get rid of this variable over here, number of states that we were computing. This is happening because now we want to leave it to the agent, or leave it to the algorithm to figure out the number of states, because it is the the environment just gives you back the raw observations. It's up to you how to encode, and depending on how you encode that information, you may get fewer states or more states, right? So in this case, we think that there are 320 different possibilities. Now the only thing we need to do is just code this up, right? So let's give this a good 5-10 minutes, and come and this is pretty much up to everyone, so you can implement this independently. But what we need is just two simple functions. One function will take something like this, and it will convert it to an integer between 0 and 320. And the other function is going to take a single integer between 0 and 320, and it will exactly return you a function that looks like this. So let everyone try and come up. And you might be able to use different types of encoding, but the only constraint is that your state space should be 320, and your decode function should be the inverse of your encode function, so they should undo the effect of each other. like this. So we need a pair of functions to encode and decode the state. So please give this a try. Look at the information. It's going to look like one of these rows. So how should we encode this so you have a distinct integer for every possibility? And then once you figure that out, then the decode function is just going to perform the opposite steps, undo what encode does. And once you have implemented both the functions, then you can just take we just generated an episode, so you can take one of the observations from that episode and feed it to encode, then feed it to decode, and then make sure that everything looks good. And the output that you could get from decode is the observation that you fed to encode. Sorry. Okay, so let's think about how to do the encoding, right? And we sort of already have the mental framework, because we know that it's made up of two things. The observation that we are getting is basically the player's state and the state of all the opponents, right? And what we also know is that the player could be in any of the 20 states, and the opponents could be in any of the 16 different configurations, right? So when the player is in state 0, the opponents could be in configuration 0, configuration 1, up to configuration 15, right? So 16 different configurations for state 0. uh, when the player is in state 1, then again you can say that the opponent can take on any of the configurations. So again, configuration 0, configuration 1, configuration 2, and all we need to do is that we need to map these configurations to different slots. So if you can think of your state space as 320 different slots, then you have to move these configurations to different slots based on what the state of the player is, right? So in each case you have 16 configurations, but they should get mapped to different positions. So probably the first 16 should go in the first 16 slots. The next 16 should go at starting at slot number 16 up to slot number 31, and so on. And there are different ways of doing this. You can also do this by taking the I'll show you in a minute. but you can also flip the roles of the opponent state and the player states. So encoding is up to us, but this is one way of doing it. What is it going to look like? Uh, in my approach, this is going to look a bit like this with some changes. Right. So one thing that we are doing is that if you look at this long piece of code over here, then I'm just converting from a dictionary to what you can say is a numerical representation, or it's pretty much like creating a bit vector, right? So I take whatever there is corresponding to north, I multiply that by 8. uh, Whatever there is, it would be 0 or 1 multiplied by 4. Whatever there is in west multiplied by 2, and then whatever there is uh, in sorry, this has to be south. Whatever there is in south, you multiplied by 1. So basically this converts your dictionary into a bit vector, and which eventually becomes a single number. Right, this is going to be unique because north is the most significant bit, and then east is the lesser significant bit, and so on. And then I take the current value of the player state. This is going to be an integer between 0 and 20, so up to 19, and I multiply it by 16 so that there is enough space for this information to be stored, right? Because there for every player state there are going to be 16 different coefficients, 16 different configurations of the opponents. So I multiply each the value of the player's state by 16, and you can see why this will work. When the player state is 0, then this is 0, and this will be some number between 0 and 15. It's a 4-bit number. It's going to be between 0 and 15. When the player state is 1, we are already starting at 16. So when this varies between 0 and 15. So the whole sum is going to vary between 16 to 31. Right. So this is one way of doing this. You could also have done it the other way, where you had the opponent states on the left hand side, like more significant, and the player states would be on the right hand side. So you could then just multiply the opponent state, like this whole thing by 20, and then add the player state, right? So in that sense, it would be that for every possible configuration of the players, there are 20 different possible states. Yeah. So this is one way of encoding, and if you encode in this way, then obviously you have to write a decode function which just undoes this. If I want to get this part out, right, I can divide this whole sum by 16, and then whatever this value will be, this is going to be my quotient, and so I can just write something like this. So I can just get the player state out by dividing by 16, right? If I divide this sum by 16, then I just get the player state. If I take the modulus, the remainder, then obviously I will get this entire thing, which again needs to be split up into the north, east, west, and south components, right? And like I said, this is up to us. Everyone can write a different one of these variations I discussed, or some other variation, but just make sure that if this implementation is correct, then you should be able to get an observation, encode it, decode it back, and get the same thing out. Yeah. So just print it on different lines. Right. So we started with this configuration, which doesn't look very interesting. I'll change it in a second. But we started over here. Then when you mapped it to a single state, we got the output 0. And when I decoded it back, then I got the same tuple, right? So this seems to be working. Let's pick, if you look at the episode that I'm using, uh, it was basically this one. So this is all zeros and zero over here. So we'll go to something more interesting. Yeah, so perhaps pick this one, which is the fourth entry in the episode. You can try three or four. Yep. So in this case, again, the player is still in state zero, but there was an opponent to its east. So this dictionary was not empty, and the encoding we got was four. And when you decoded it back, you got it correctly. And we can try it with other, custom inputs just to check that this is working correctly. But if we implemented this thing correctly, then the rest of the code almost runs unchanged. The only thing that we need to change over here is the number of states, which for the time being we can just hard code to 320, because we know the way we are encoding things. This is going to be 320. This is one of the changes. And the other change is going to be that you don't want to use the state, the observation s. So just you will have to wrap this as in a function call. So this is an integer, right? And this is nothing but sort of hashing where you're taking uh, an arbitrary input and then you're mapping it to an integer, so you can easily retrieve it and you can easily store it. But yeah, with these changes, it should be really straightforward to train the algorithm. There are no other changes because the algorithm and everything remains the same. The logic remains the same. The only thing that is different is that now you need to encode your observations. Earlier, the observation was just an integer, so we were using it as it was. Now we need to do the encoding. Okay, this will take a while. What is really important is going back and looking at this. So in this case, we decided that we will have this sort of a setup where we are just passing five different bits of information. Uh, but this introduces a lot of additional complexity, and this is basically what we will be doing in the entirety of course too, where you are going to look at, if you think about deep reinforcement learning, it's basically looking at more complex types of environments where the whenever you sense the environment, the state is going to be complex. Like it could be an image, it could be a a stack of images, a bunch of images, depending on what you are looking at. So there's going to be a lot of pixels, millions, several thousand, you know, several millions perhaps, depending on how many frames you're looking at. But typically, for example, if this was a video game and I was just looking at the screen of the video game and trying to train an algorithm, then I would be looking at several million pixels. And one of the fundamental issues there is, how do I boil that information down into something which is more like an integer, so that I can, even though we won't exactly be using a table, but the idea is more or less same, that we need to encode the state somehow so that we can learn important mapping between the state and the action. And really the whole idea is that you can use a neural network to take observations and map them into states and actions, right? So it's very, very similar to what we are doing here, but because of the added complexity of the observations, you cannot construct a table, and two, you have to learn to encode. You probably cannot come up with a scheme like this which is hard coded, so you have to learn to encode that information, right? It seems this loop is over, so yep. Pretty print will not work, right? Why will it not work? Because now the state has a lot of information. Even if you are using the encoded state, it is giving you a number between 0 and 320, and there is no very straightforward way of seeing how to visualize that, right? So you do want to see what action gets taken, but this pretty print will not help you take that function. That is sort of something that we need to figure out, and it's important for this exercise. It's also important if you are attempting the project to first of all figure out pretty print function or a debugging function that lets you visualize what the policy has learned. Right over here, I can't tell you whether this has learned something useful or not. The only thing I can do is I can just put this policy into action, let it play a few games, and then see whether this policy is learning to play the game of football or not. Right. So this simple couple of changes which we first made the state space larger by allowing more pieces to move, but then we also curtailed on the amount of information that was flowing out. So now it becomes very difficult, because if you think about how you're going to write this function pretty print, so pretty print doesn't know how it is just going to look at the observations, right? So it knows where the player is. It can, okay, position the player. You just use the decode function, find out where the player is, and position it on the field. You can also find out how many opponents are present, and you can represent them with the jerseys on the field. uh, and what you don't know is where are the other agents present, right? And so that is something that you cannot print, but with whatever information is available, you can print that, and then you can print what are the actions corresponding to that policy, that position, right? So you will really have to think about whether you want to print 320 different snapshots of the field, because there are 320 different states, and if you want to print out the policy for every state, then it's a lot of information to absorb. Or if you want to use some sort of a trick and look at, visualize limited input, that is totally up to us. And what we could do is, what we need to do is basically implement try to implement a pretty print policy that sort of works for you. If you look at the solutions branch, there is already a pretty print policy function. It has its own approach, but it is at least able to print the actions that I'm taking in different sort of scenarios, right? So it will help me visualize what actions my policies are taking. But we can definitely try the other approach, which is uh, just letting the policy play, right? So that is uh, that is something that we can do. Let me try to do that. It's going to copy over the code. So we just trained a policy using 5,000 steps and the episodic approach, and we just want to see if, right, this is nothing but I generate a game of football, and then I am going to follow the policy, right? This is the greedy policy that we want to follow once we think that the table is trained properly. Again, for using the policy, we will have to use the encode method over here, because we need to look up a table. Q is not defined. Yeah, Q is definitely not defined. Right, and depending on, because it's random, you might see a lot of actions being generated, and it produces a lot of output. So one thing is clear, that this is not a very perfect or efficient policy. I don't know how many thousands or hundreds of steps it has taken it, right? So it has taken more than 5,000 steps, uh, but you can see that the ball is just stuck there taking action x is just not budging from its place. And long time it is just not budging, which means the policy is almost as bad as what we started with, right? But now we must be able to visualize this. We must be able to detect what is going wrong. Why isn't the policy learning? Is it that we haven't trained for enough steps, which is expected because now it's a more complex environment? So yeah, so somewhere in between it tries to escape. This is an interesting part that helps us in debugging. So till this point, it was in the first cell, it was always trying the same action X, um, because of course now the policy is trained, so it's deterministic, it's greedy. So the policy is perhaps it has perhaps learned to take action X when state 0, and it has been doing this for several thousand steps. But it was stuck here until this point when what happened over here is basically the step sort of didn't really execute, so it still wanted to stay put in the cell, but it actually slipped, and that is like a blessing because now it was able to break out of that jail. And then I don't know why, but it goes back into that jail. But you can see that on its own, just don't want to scroll through the entire output, but on its own right now, with 5,000 episodes of training, the agent takes a really long time, and it's only able to get out of these uh, silly situations where it is stuck because it's not taking the right action, because there is some slipping environment, right? So at the end it is able to indeed convert a goal, and it has taken it 539 steps and resulted in a very negative reward of minus 65, right? Why exactly this is happening, that is something we need to figure out by debugging it. Of course, having a predefined policy will help, uh, but yeah, we need to figure that out. And right, so next thing we can try is the TD approach, and perhaps it will make a difference now, because earlier we saw that okay, perhaps it was taking 5,000 steps for our previous environment, for getting a policy, but now that environment is far more complex. We haven't really figured out how many thousands or hundreds of thousands of steps are needed to train a policy when you're using the episodic approach. Sorry, I don't want to scroll all the way up, but let me just close now. Right. So for this code, the episode-based approach, we haven't really figured out how many episodes are needed, what should be learning, what should be the decay rate, and what should be the value of alpha. But it certainly isn't working with 5,000 steps, so probably it will be 10,000, 50,000, whatever it is. But then perhaps the TD learning approach will take you fewer steps to do the same thing. Yeah. Again, this has to change. So change it to 320. And again, this is going to be, sorry. So again, we have to replace all instances of wherever your state is occurring. You have to replace that with encode observation. This is your sarsa, so you have to encode in 3 different places. Right, with this change, it should be able to run. Mhm. Okay, something is going wrong. Oh yes, Yes, here too you have to pass it. Right, so everywhere that you're using the state you need to know. Okay, in code observation. Oh yes, there are very subtle changes that you will have to make over here. This so we were directly reading the initial state, which is not the right thing to do. So this had come over from the previous implementation. Now this is going to be different. So if you directly read the state, this is going to be a tuple. But if you call the reset method and then read the state, this is just going to be the observation. Right. So these changes have to be made. You have to figure out these small changes. This is, of course, this wasn't the correct way. So although we were directly using init state, the correct way would have been to just call reset and read the output, because reset was always returning the state, the initial state. So that was much needed. But the other change pretty much is replacing all instances of states S0 and S1 by uh, yes, by replacing them with a call to encode state. Right. We can let it train. It will take a while, but the really interesting, the really interesting part is that now we have made these changes. We can go back and think about what other changes can be made. Right. So we will get a policy, and I'll just paste the code again, and we will see how well it performs on in terms of how many steps it takes to play a game of foosball. And but now you can there are many interesting things that you can do with this kind of setup, right? Because now you can go back and enable the players to move around, so let them move horizontally as well. That would be one change. You can increase or reduce the radius to which your player can sense. That would also mean changing your encode and decode functions, but you can change that. It would be nice to have a function that so you can pass some sort of a parameter to the to the foosball class, and based on that you can set different uh, radii, right? So if you set it to 1, then it just gives you 4 cell. If you set it to, I don't know, something else, then it gives you the 8 adjacent cells. If you set it to some higher value, then it gives you, it lets you see even further. So we can implement that. You can make the field larger, more maybe 50 by 50 or something, and introduce more opponents. You can also introduce more agents. Of course, you'll have to figure out a different way to render it, because you don't want to display two balls on the field. Uh, but those are the changes that we talked about in the beginning, when we was saying that we'll take an environment and over time we will tweak it uh, to uh, to until and it will have all the flexibility, and you would even be able to make it look like the Google football environment. So we're not quite there yet. It's a lot more complex environment. But if you read about the Google football environment, then it actually lets you sense the environment in two different ways. right? So one is the typical way, like you just look at the screen, whatever is going on, which is uh, which is probably eventually what you want to be training on. But it also sort of uh, lets you look under the hood and capture the underlying state, like which is pretty much like what we are doing right here. So you can capture, for example, the integer coordinates or whatever information there is about where the opponents are, where the goalpost is, where the goalkeeper is, stuff like that, in a very simple way. So you don't need to process entire images or the video feed, right? So uh, that because that is possible, you can train an agent which looks like this. Probably the table is going to look a lot bigger, but you can train an agent which is, yeah, so train an agent which is going to look pretty much like this implementation, but it is able to play a game of football, right? So I'm just running it for another time because there was one line that was crashing. But in the meanwhile, you just copy paste this code. Now we want to evaluate if Sarsa is able to do any better. Remember last time it took us 500 steps to break out of that jail. So this is the only change that we need. And all the debugging steps that we talked about previously in the previous sessions, they are going to come in handy right now, because now there is no easy way of visualizing everything. So you do want to have a predictive function that gives you some hints, but more importantly, you need to be able to look at what is happening to your reward over time. And typically the way you do that is by averaging the reward over some number of steps. So perhaps you keep track of the reward over the previous 100 steps, and then just plot it and see what is going on. Is the algorithm even learning anything? Is there something wrong with the algorithm? Seems to be learning or not? uh, with the q learning approach, the first time I ran it, I tried it. It gives me a fantastic result, just 11 steps taken. And now we don't necessarily know what the shortest route is, although you can figure this out using a deterministic algorithm. This is certainly not going to be the 5 or 6 steps that we figured out earlier, because now the agents are moving around. So this can be arbitrarily long depending on what configuration the defenders end up in. But 11 steps seems really short. We can run it a few more times. Right, I can even stop rendering it just to see, how this is, just to look at the number of steps. Right, so it takes me 8 steps, 7 steps, 18 steps. Again, we don't know if this is the best policy, but this is way better than what we were getting with this episode based approach, right? With just 2000 steps of sarsa, we seem to be performing really well in this environment which has so many moving parts, right? Now whether this is the best policy, this is the one where you should stop training or not, that is up to us to figure out. uh, yes. Then we also can train, we can do the same thing with q learning. I'm not going to do that because it's just a matter of changing uh, encoding over here, right? So the key takeaway sort of is that even with this amount of dynamism and uncertainty, the algorithm remains unchanged. The parameters, we may be getting lucky here because we didn't change any hyperparameters and we're still able to get so far quickly, but that will require debugging, right? So try to understand whether your algorithm is learning or not, if it is learning fast enough. uh, are there certain configurations that are causing problems? So we will have to figure
So
out that. Go ahead.
So Farhan, I think the idea here is since the first column does not have any players, right? I means opponents. I think go till the south of it, and then you try to go to the goalpost. So that kind of thing probably it has learned so that it is reaching quickly.
Yes. So the first column, of course, doesn't have any opponents, and the opponents cannot go south. So probably it makes sense to go, down until you find a gap, and then you go east. But because they are eventually, like, they are able to move up and down, so you can never predict what will happen when you are going south. So this is this agent is never going to learn a perfect policy because it's not able to look at the entire field. And this is really interesting because we don't want it to see the entire field, but can it, with the limited amount of information, can it still learn a policy where it can avoid the players? And there are literally so many things that can be learned. And when you debug, you want to see how is it avoiding the different configurations. If there are configurations that trap the player, is it able to sort of break out of them? All of those things. uh, and that will just require debugging and digging down at least one level deeper and looking at what policy is being learned, right? But the important key takeaway is, again, two things. One is the encoding of the state is, in a real world, it will be on us to encode the state properly. And number two is basically that you won't have access to the underlying, the full state in most of the cases. You have to learn to deal with the partially observable state, and hopefully that will have enough information to let you make decisions which eventually are optimal in some sense. So in this case, as long as it's able to find a short path and it doesn't collide, it gets me a good enough reward, then I'll consider it optimal, right? Yep. So I think with what we have learned today, that some of little bit of it will perhaps come in handy when you are attempting the project, because the project is, again, although the environment in question already encodes the state for you. uh, One, we have learned why is the state being encoded in that fashion, to keep the state small enough, state space small enough. And two, we know that although the environment is doing that for you in the taxi case, if you want to take a real problem and you want to convert it into an environment like of an API, then probably the encoding is going to happen. I mean, it's up to you, but you typically want to keep the encoding outside, because encoding also depends on the algorithm that you want to use. So uh, and generally you will just get raw output from your environment, so you need to process it and code it. That is sort of the key takeaway, right? Now everything that we will learn in codes 2, that is going to build upon this case, right? So we are going to straight away and jump into more complex problems where the state space, even in this case, if you make the state space much more larger, I don't think you will be able to store that in a table, and then you have to start thinking about how to replace that table. And you can't use the table, you cannot come up with an efficient encoding system, right? So that is where neural networks will help you do both of those things. And when you introduce neural networks, then there are other things, other issues that come up, and how to deal with that. But even before jumping to neural networks and deep reinforcement learning, there are lots of other lessons to think about over here, right? And we will only learn those lessons by playing with the environment, by looking closely at the queue table. Are there entries that are never getting filled, and are there trap situations, and lots of other things to explore here. Cool. There's really nothing else that sums up today's session. Like I said, you would want to look at the solution notebook, which has cleaner versions of these implementations, and I think it actually does also have a pretty print function. Again, not a very helpful one, but it is still able to work. You can adopt that, you can write your own. um, the other thing is that we will have a follow-up session, sort of a wrap-up of the entire course on Thursday. Now that is strictly not part of the course because the part of the course is roughly exactly 4 weeks. So we had all those sessions. So it's optional, but still highly recommended because I'll just do a walkthrough of everything that we learned in this course, and I definitely want to go through the slides and talk about the Billman equations, which we have been avoiding for so long. So again, there isn't going to be a derivation or a proof of the Billman equations, but just what those equations are and how do those equations map to what we have been doing. So whenever you're going through the literature, books or anything and looking at them, then that makes sense to you, right? Uh, Project deadline is 21st again. If you're not able to submit, please do let me know, and we will accommodate everyone. We will give you extensions, but it's really important to finish with that project. There are lessons to be learned by doing that small twice project. Still, it's complex enough to give you some good insights. Any questions, doubts, confusions?
Hi, Farhan.
Hey.
Uh, yeah, actually, I have seen during this project the average reward is not so good metric to decide on the episodes, because in that example, what happened is like uh, even the average reward graph became flat.
Mhm.
Uh, the outliers are impacted more because the reward they give is -100, and
Right.
like suppose in 2000 every reward is low, and then the outliers reward is also negative, reward is also impact is less.
Mhm.
At the end, the reward of the best case is very good, but due to the -100 and those kind of thing, it
Overall
became
is flat.
flat. And yeah,
Right.
so means like, can we do something like weighted average or some weighted average or
So we were
weighted?
also tracking the percentiles, right? The bottom 5 percentile and the top 5 percentile.
Yeah, yeah,
So
yeah. But I thought like that is just to showcase. I haven't used that metric, but I just
yeah,
used.
so the idea is same that when you're taking the average, then average is of course going to be influenced by a lot of factors. What is the outlier? How many outliers are there? What their values are? So if you are able to get that the bottom per percentile, if that is good enough, that gives you a better signal than looking at a single number, which is your average.
Okay. And one more thing, like Sasa performed very badly in the taxi project compared to QLM. It is never converging. Even I have tried with 10,000 episodes. I couldn't
That
find the reason, but I have tried comparing with BFS and
yeah,
done things, but it is never converging to the BFS thing.
there could be.
So
I mean, I haven't looked at your submission. I will start Friday. But what I saw from the submissions from the last batch was that there were very subtle bugs sometimes, and it happened only with Sarsa. So almost everyone got their Q learning, and many people tried Q learning, Sarsa, and expected Sarsa, all three implementations. So the Q learning and expected Sarsa were converging, and Sarsa wasn't, and there was always some sort of a bug somewhere. So uh, we can, I think, look at that. I'll see, I'll check if I can catch the bug, but it's likely because of a bug, because I have seen implementation, and I did my own implementation using Sarsa, and there are, depending on your hyperparameters, it does converge between like 5,000, 10,000, 50,000 episodes. It does converge to the correct solution.
okay, yeah, I will check it once I like if I find anything related.
Sure. Okay. Anything else we want to discuss? Because otherwise we are over time. We can wrap up. Again, I'm available on Slack. Please let me know when you're going to submit the project. Whenever it is, just give me a tentative deadline and take a look at the project. It depends. You can also sit down and finish the project in like 4 5 hours, or you can split that time over many different days. uh, it will just depend on how much what sort of a deep dive you want to do. But just getting the basic hitting the metrics right and getting the rubric requirements right, that shouldn't be very complex. You still have to like play around a little bit. Cool. If there's nothing else, then I will wrap up. And please don't hesitate to ask questions. I'm available on Slack or email me. Let me know when you intend to submit the project. Thank you.